Hello and welcome all of you. Today, I'm happy to present our paper Sponge Poisoning of FPGA-based DNA Accelerators in Differential Private Federated Learning. Myself, Mohammad Shakir Akram, along with my other co-authors, are happy to present this in IEEE host conference today. The outline that actually covers whatever I'm going to discuss throughout my slides is background, what federated learning is, how actually it is important, and then how FPGA fits into a federated learning, and then what can be the free rider vulnerabilities, and then EvoWeight sponge poisoning technique that we came up, and then the results, and then their impacts on federated learning setup. And finally, I will conclude the whole slide and the idea and the findings that we came across. So starting with the federated learning, whenever we talk about the data privacy or regulatory effects, data sharing is always a concern. And when we talk about AI models, any AI model, it needs the data. The more data we have, the more and the good data we have, we are very good in our AI models training and then getting output out of that as well. So it means data is very important, but when there is a privacy concern or a security concern, we can't share it. So federated learning comes up with a solution that you train your model uh, at the edge where you actually got your data, right? So you have your data, keep your data with yourself locally, train it, and then only share the weights. So you only share the weights to the global server, which is actually going to aggregate and then send it through to all the models. So every user in the system is actually collaborating to have a single global model to actually improve its accuracy as well as its diversity, right? And then when we actually talk about the edge, it's not just about the data privacy. Even in the centralized training, when we are actually sharing the raw data, so raw data actually involve lots of other things as well. Like there's a constant communication happening, there can be a latency happening, there can be a very huge data chunk that is going to be shared up and down. So that actually involves lots of communication, power losses, latency, and those kind of stuffs, right? So let's talk about the weight that's going to be shared. Does it save? Yeah, it actually reduces the raw reduce the privacy leaks of data. We have kept the data locally, but still there is a concern of data leaks using these weights, which people are doing using reverse engineering or those kind of stuff, right? So what the other solutions are? The other solutions to that are encrypt those weights with a differential privacy, secure aggregation, homomorphic encryption, fine-tuning, and outliner analysis at right? What it does is basically actually going to encrypt those weights that are going to be shared to actually reduce that leaks of the privacy as well. So it ensures that the data is all sitting on locally. It's not never been shared with the global server and never been shared with other users, which can be with the competitors in the field as well. But the way that they were sharing is also secure and private. So moving forward, when it's actually happening everything on the edge, as I was talking, there are few resource constraints. Why, if I talking about the resource constraint, is there are at the right time, current time, there are lots of edge devices which actually getting the data, they're generating the data, they can be able to process the data. So to process the data, they have the resource constraints, and with the edge devices like for ECG, we have 300 million ECGs which are being collected annually, but we're still short of data because of those data cannot be processed at the edge, or we don't have a good system in place at the moment. So the thing is, limitation at the user end is resource constraints, latency, power consumption, and computations, right? So edge has its own limitations. If we want to bring the computing on the edge, so it has its own limitation. For that limitation, the FPGAs or hardware solutions comes up as a solution. So what FPGA does is actually going to contribute for the training as well as for the inference at the edge. And when we talk about the FPGA, because it has parallelism, it can support quantization, and it has a reconfigurability support as well. So what it actually helps, it actually makes a very specific hardware is going to be a very small size, which can reduce their power, but can do a very fast communication processing of that data on the edge. So training on the edge, then inference on the edge, both happening on the edge can be supported by the FPGAs. Like our previous work was actually based on that, which actually does this federated learning thing, right? So moving forward, weights are being shared. What is free rider? There can be a free rider. We actually kept ourselves we actually made sure that okay, our edge devices are intact. They are actually doing a very good processing, and they're doing the training on the edge. They're not sharing the data, but they're sharing the weights. Those weights are also encrypted or differentially private, or there are lots of protocol that we discussed are placed, right? What if the vulnerability starts from inside the system? That's another thing, right? So free rider attacks are those things like someone not intruding from outside. It's basically someone sitting inside. Because how it can be done is basically from a sponge poisoning and crafted weights, where some of the weights are being crafted, which are being communicated between the users and the cloud, right? For the collaborative learning. So the idea is basically how pre-rider vulnerability can happen is basically at initially the collaboration is happening between these systems, right? They're always collaborating with each other and getting a good accuracy of the model as well as a good diversity of the model. And at some stage when this user becomes a free rider, is actually happy to with that accuracy and diversity with itself, but become vulnerable to the system. What it does is basically starts generating the evolutionary weights and then sending it through to the global server. And then actually, whenever the global server aggregates those weights and send it through send it through to all users, and then because that user is a free rider, is aware of that thing, is actually discussed that. And then rest of the users actually use those poison weights, which actually going to impact their power, which actually leads to a temperature, battery life, as well as their performance in terms of latency, throughput, as well, because it's actually doing the more computation than expected, right? And depending on like if we have lots of other edge devices which have different resources, so the ones having a very small resource will be affected more, the ones having a higher resource will be affected less. So this is a vulnerability which we came through, and then we actually went up, okay, how can be crafted, because there are different things in line which actually stops the security leaks and privacy leaks. Even the outliners that are there, that whenever there is a deviation between the accuracies, so those weights are never being incorporated into that system, right? So moving forward, we came across, okay, let's bring up a solution which actually going to keep the accuracy intact, because by keeping the accuracy intact and because of the privacy and those things, the user is always secure, its data is always private, they are never been known to the users or the other users in the system, and to the global server, whoever is communicating where the data is coming, they are all collaborating, because it actually relies on a trust, right? So moving forward, we will talk about the EvoWeight, how this approach can be done. So what we did is basically using the EvoWeights, we did a binary convolution on a binary convolution neural network in which we had the weights in a binary form, ones and zeros. So what we did is we tried to switch or flip the weights from ones to zeros and zeros to ones, and I actually tried in a closed loop try to assess that, okay, how much it's impacting the accuracy to keep the outliner intact and to remain undetected in that system. So why this flipping is important, because when you're talking about FPGAs or a binary convolution neural networks or a binary DNNs, the ones and zeros actually somehow in the hardware are actually dealt with XNOR pop count operations. So the purpose is to increase those XNOR pop count operation and keeping the accuracy intact. So number of XNOR pop counts to increase, it's going to impact the more computations than needed, and it's actually going to impact the power and the other things in line, right? Okay, how we actually do it is basically an algorithm. Initially we have a clean weights after initial collaboration, as we saw in the last slide. Then we actually go set a threshold accuracy that we don't want anything to be dropped down. We set it at 1.65 in our case, and though we were still got the full solution which was only impacting 1% of accuracy. And then Dinan leaves, and then mutation rate to cover the range of weights that actually going to flip the weights from 0 to 100% of that specific layer, and then going to assess the accuracy and power impact on regarding that, right? So output is going to be definitely a crafted weight which is going to come up, which is actually that specific free rider is going to communicate between the cloud and himself. So initially with a very clean weights, Then comes the main story where actually we are going to do the mutation for increased firing neurons. Firing neurons are going to be increased, and each increase is going to be evaluated based on the power consumption and accuracy. And because we have set the threshold of accuracy, so whenever the accuracy is less than that threshold, because it's going away from the outliner and the outliner can detect it, so it's going to be discarded. Those solutions are not going to be discarded. So only the top key best solutions who are actually going to pass the fitness test is going to be selected. And finally, we are going to combine the layer-wise selected solutions into one updated population, which is going to replace the clean weights with the top performing alternate solutions. So finally, when we have the combined crossover layer-wise solutions, we are going to test its effectiveness in terms of overall data set which we have. We took a very large sample size, which is 45,270 samples for accuracy, and assess the effectiveness of sponge pardoning. And actually, is it still actually keeping the accuracy high and it's not impacting overall to the system. So we have a best performing crafted weights in the end using that algorithm. So this is what it comes up. So for each layer we have the solutions, right? But what we also came across is basically, because we have 6 layers, 3 linears and 3 convolution layers, to assess like which layers are more affected. So what we also came across is basically these linear layers are more vulnerable to the Evo crafting weights rather than the convolution layers. And it is actually suggests us that any model that is going to be more having more linear layers or a high number of linear layers is more vulnerable. Why I'm talking about this is basically when you see deep down is if we set the accuracy in our case is 80% as a threshold, so we can see that there is a dip down for the convolutions, but linear somehow try to manage on that level. Like for example, this specific layer is still at 80% at a very high percentage of flipping weights, which is about 20%. So this is how we actually came across for each layer to actually measure and assess what exactly is happening. So we did the 15 different combinations of those experiments for EvoWeight to actually find out the optimal solution. So that algorithm is repeated for 15 different experiments, which includes random, manual or random, ascending order, descending order, and all other cases which can be possible to actually identify the best solution out of it, right? And then once we had that, we came across what is it's impacting in terms of sponge bonding on the system performance across our techniques, whatever techniques we had from experiment 0 to experiment 15, and how much actually we flipped the firing neurons overall. It's not about the specific layer, it's actually overall neurons that we flipped. So it actually shows if you see the accuracy, which is very down in terms of rise, which actually meant not to be a drop in accuracy, which is actually very low, falling less than 1.06% overall, and it's impacting not only power but runtime. It's actually impacting the throughput. It's actually impacting the overall influence of accelerator, right? This is what we came across. And then moving forward this experiment into a federated learning, we had different combinations on which we tested. We started from 2 users to the 5 users. So 2 users, one become a free rider, how much is going to impact the weights in that collaborative learning. Then 5 users from one free rider to the 4 free riders, how much it's going to impact. So we came across and we saw that over the rounds, 10 rounds of communication between the different combinations of a federated learning between the users and the cloud, and how it was actually impacting the power consumption overall of the system, whichever the other users are involved in it. So we came across and we saw that it actually all the way through in all the rounds, somehow the EvoWeight was able to actually bypass the security and privacy and those outliners protocols, and was able to impact on the power and keeping the accuracy high. So finally, we are going to conclude this study addressed the shortcomings of traditional model replacements and gradient poisoning attacks that has reliance on crafting sponge examples and costly backpropagations. So we are not relying on any backpropagation training, which is going to happen, which is definitely a costly thing. And then we don't need any data set. So we haven't crafted, we do not need any data set to be with us to actually craft it. So without having any data set, we are actually somehow able to do this crafting, because we only got the weights from the global model. That's what we needed, and then we actually try to manipulate with that. Other than that, we actually involve a model which actually involves biases, weights, convolutions, linears, or covering a whole range of weights. And we present this strategy in fine-tuning enabled differential private secure federated learning, which achieves 6.7% of neuron activation and up to 17.4% increase in power consumption, while limiting accuracy reduction to only 1.06, actually negatively impacting other performance matrices as well, which is increase in inference time, runtime, and reduction in throughput. The attack can lead to potential higher temperatures, potential denial of service, and system crashes, and reduced device lifetime. Our findings also reveal that if you have more neurons, deeper layers, linear layers, and a higher proportion of linear layers are particularly more vulnerable with their reduced sensitivity to weight manipulation. Models with higher precision can exhibit increased vulnerability to EvoWeight type attacks, particularly in architecture dominated by general matrix multiplications. So thank you so much for listening. I hope you liked it. If you have any question, please came across. Thank you so much.